Okay, so last class we defined this sort of concept of an abstract vector space, which is a space just like we're used to, only instead of vectors we can have other things, and we gave some examples. The set of n by n matrices and the set of polynomials of up to a certain degree. And so here's the definition again. But one thing that we also mentioned in class was that a lot of, or actually all of our concepts that we had developed for regular spaces and subspaces also extend to this abstract concept of a vector space. And in particular, I want to define what it means to be linearly dependent and independent within a vector space. So I'm going to let S equal a set of objects or vectors, and I'll just go ahead and denote them as vectors like we've been doing. And I'm going to let this be a subset of a vector space V. And then I'll say then S, the set S, is linearly dependent if there exist scalars C1 through Cp in R, not all 0, so some can be 0, such that C1 times B1 up to Cp times Bp equals 0. And so we've seen this definition before. This is the same thing, only now these are objects instead of vectors. And so we could have matrices or things like that there. And otherwise, we'll say that S is linearly independent. And in this case, then C1 must equal C2, must equal C3, up to Cp must all be 0. And in this instance, we can also talk about what it means to have a basis. So we'll say, definition, that the set S of objects in V spans a subspace H of a vector space V if for every object Y in H there exist scalars C1 through Cp such that I can write Y as a linear combination of the elements of S. Okay, and again, we've seen that before too. Now it's just under this new umbrella of a vector space instead of just a regular space of our subspace of Rn. And further, if the vectors or objects in S are linearly independent, then S is a basis for H. And this we talked about in class. So for some of these new vector spaces, like the matrices or the polynomials, we talked about what a potential basis would be, and we sort of argued why the objects we were putting in that basis were linearly independent. But here we are stating formally just that these definitions and these concepts do carry over. And lastly, I'll say too that if I have some basis for my vector space, and then I can write an object as a linear combination of those elements, then that representation is unique, just like we saw before. And so this idea of having a coordinate vector also extends to the vector spaces. And lastly, we can define what it means for a transformation between vector spaces to be linear. And so I'll write that. So definition, and I'll say a linear transformation T from V to W between vector spaces. So vector spaces V and W is a rule that assigns to each vector or object in V a unique vector T of X in W such that the following holds. And so we've actually seen these before. It's the same thing, that the same two criteria that we had before for linear transformations, just now with vector spaces. So if I want to take a transformation of two objects or vectors u in V or u plus v in V, then I can take the transformation of u plus the transformation of v instead. And similarly, if I take the transformation of some scalar times a vector u in V, that's equal to that same scalar times the transformation of u. And again, I want for all C in R and B in V. And one thing we did talk about in class too is that we defined our vector spaces over R, real numbers, but that doesn't necessarily have to be the case. So if I wanted to extend it to the complex numbers or some other collection of objects that have a certain property, I can do that. And one last thing that I want to do in this video is go back to an example from class when we were first talking about different subspaces. And so our example in class was this R infinity, which is a space consisting of infinite sequences. And so something like 1, 2, 3, 4, and so on is an element of this R infinity. And we said that this was an infinite dimensional vector space. And what I want to do is talk about a sort of interesting linear transformation from this space to itself. So I'm going to let T from R infinity to R infinity be the transformation, or actually, so it's a linear transformation, be the linear transformation, such that if I have T of a sequence, and let me say A1, A2, A3, and so on, I'm going to make this equal to A2, A3, A4, and so on. So really what I'm doing is I am just chopping off that first element. So specifically T of the sequence 1, 2, 3, 4, and so on is then equal to 2, 3, 4, 5. And one thing that's interesting about this is that this transformation is onto. So for any infinite sequence you give me, I can find a T that gets sent there. So for example, if you give me the sequence 5, 6, 7, 8, and so on, then T of 2, 5, 6, 7, 8, and so on, or 3, or 4, or whatever, will go there. So this transformation is onto. However, T is not 1-to-1. For the example that if I sort of reverse this, we saw that multiple things went there. And what's interesting about this is that this cannot happen in a finite dimensional vector space. So this can only happen in infinite vector spaces, which is quite interesting. Okay,